We ended last week's presentation talking about how a force is not actually merely a quantity. It's not like your mass. It has a direction to it. Force acts in a direction. It is a vector, not a scalar. In physics and engineering, scalar refers to something that can just be described with a number and a unit. Power, for example, is a scalar. There's no direction to how many watts your computer is using. Mass is a scalar. However, force and velocity and acceleration and momentum are vectors. They have magnitude and direction. You can think of force as an arrow. Arrows have length and direction, so do forces, so do any vectors. We're going to be adding forces, but we should think why add forces. The reason why you add a force is because of Newton's second law, which tells us the relationship between force and mass. That's right down here, the second law. If the sum of the forces is not zero on an object, that means that the object, in our case usually the barbell, will move. It will accelerate. Its velocity will change. If the direction and magnitude of the movement is non-zero, the acceleration will be proportional to that force and in the same direction. So if I push on you and I overcome the force of friction, you're going to accelerate in the direction in which I'm pushing you. So this formula here, this is the sigma. Again, it means the sum of. You're just adding up all the force vectors. The F and the A mean force and acceleration. They're both bold-faced. That's a convention for making things vectors. You can also put a hat on the top of them, a line. And you can see that the sum of the forces is proportional to the acceleration, which is going to be in the same direction, and the mass is the proportion, which is a way of understanding mass. The more massive you are, the more you resist forces. Knowing how to add forces will help you understand what's going on in the barbell lifts. This will help you coach better. You're not going to be doing trigonometry calculation. You're not going to be sitting in the gym with your calculator doing these sorts of problems. However, having done them, having thought through them is going to make you a better coach because you'll be able to see and understand what's going on in the lifts. It's going to help your intuition. So when the sum of the forces is zero, the thing will not move. Technically, it will not accelerate. If your spaceship is hurtling through the void and there's no net forces on it, it's just going to keep hurtling. It's not going to accelerate at all. But this rock isn't moving. And if the forces up and the forces down are equal, and there's no sideways forces, it's not going to move. Often we have straight line forces. In barbell training, we're worried a lot about gravity. So in this picture of this deadlift, if the red forces of gravity add up to be bigger than the blue forces from the lifter, the barbell goes down. If the blue forces add up to be bigger than the red forces, it goes up. If they add to zero, it doesn't accelerate at all, and it'll either continue in its motion, or if it's not moving, it'll continue not to move. We've all had that point on our deadlift. So now we need to talk about how to add forces. You can do it graphically. You get pencil and paper and a protractor and a ruler, and you draw your vectors on the paper and measure up the answer. So you'll draw the arrows to scale. This is very important. So you'll have to pick a scale and then make, say, a 50 Newton force will have to be 50 units long on your graph paper. And you'll do it head to tail, and you draw the next one with its tail next to the head of your first vector. And the line from the end of the last vector to the tip of the first vector is the result. this is simpler to think about, it's harder to do. The better way to do it is harder to think about, but easier to do, and that's to do it trigonometrically. You may have had trigonometry in high school. It's not as bad as you remember it. Don't be frightened. It's not that hard, really. Trust me, it's not that bad. So here's how you would do it graphically. In fact, I did this graphically on my design program. I just drew a bunch of arrows and I dragged them with the head to the tail, and then I drew the white arrow from the end to the tip. And this white arrow is the sum of these vectors. It's easier to do on a computer than it is on paper. But it's not that easy. So here's a little bit of trigonometry. Just a little bit. There are two functions that you need to know about, and you don't need to know much about them, but you do need to know them. We have something called the sine and cosine, and both sine and cosine take as their argument an angle. They're angle functions. And the way to understand this, we have a unit circle. Okay? A unit circle is a circle with a radius of 1. That's all that means. So here you can see the radius. The length is 1. So far, it's pretty simple. Theta here is the angle between this line and that line. The more you go around the circle, the bigger the angle gets. There's 360 degrees in a whole circle. Now, what the cosine is. If you see this blue triangle, the cosine of the angle theta that this line is at is the distance from here to here. That's all it is. The sine of the angle is the distance from the x-axis to that point on the circle in the y direction. And as this little guy walks around the circle and drags that line around the circle, you can see that cosine and sine will change because the circle will change. Now, the uses of this, well, we'll see the uses in a moment, but you can guess, and all you need to know is a few things. That if the angle were 0, if we flatten this line down to here, the cosine of theta would be 1. The distance from here would be 1. The sine of theta, if we collapse this line all the way down to 0, the sine of theta, if theta equals 0, would be 0. Okay? This is going to be useful to you when you're thinking about directions and angles in which the muscles are pulling on the joints. Sometimes there's a better angle, and this will help you figure it out. We'll talk about it a little bit more momentarily. So component vectors are very useful. So in trigonometry, the vector can be resolved into orthogonal components. Orthogonal means perpendicular. It's useful to do it in the x and y directions, and most often, this will be in the horizontal and vertical directions. Next week, we're going to do it along the length of the femur, so it won't be horizontal or vertical, but it'll be useful. But just stay tuned for that. And what you do when you're adding vectors, you add all the x components, and you add all the y components. And these are the x and y components of your component vector, of your resultant vector, pardon me. So you just add up the x components, the y components, and you get the x and y of your sum. And so here's this vector of length L. Well, the components are real easy. So you get out your calculator, which will have cosine and sine buttons on it. May have to play with it and get used to how to use it. Then what you do is you take the length L and you multiply it times the cosine of this angle, and that gives you the component of this vector in the x direction. You do the same thing in the y direction with the sine rather than the cosine. Now, I want you to pause and think about the bench press. Think about the fibers of the pectoralis major as they are attempting to drive the barbell up. If theta is very small, if you have a lousy bench press arch and all those fibers are laying flat on the ground, what will the component in the y direction be of the force that those fibers can apply? It will be very, very low. It'll be almost nothing. If you can arch in the bench press and get that angle closer to 45 degrees, you get a whole lot more force in the y direction, which is what we want, which is why in the bench press you need to arch. So that was a little practical consideration of trigonometry. All right, so this is an example, this complicated picture, it is an example of adding in two different ways. So I am adding the red vector, the green vector, and the blue vector together. On the left-hand side, I just dragged them and then drew the orange from here to here. The red vector has length L, the green vector has length L2, and the blue vector has length L3. And we're going to consider these thetas are different for each triangle. Okay? So you can just add up the components in the x direction, which is L cosine theta of this triangle, L2 cosine of this theta, L3 cosine of this theta. And you do the same thing with the vertical components, which is L sine of this theta, L2 times the sine of this theta, and L3 times the sine of this theta. And you add them all up. I kept track of the minus signs for you because sometimes it's adding in the other direction. And you can get your resultant vector just from addition. In the end, it's simpler. Okay. In barbell training, force vectors will be vertical. But on the joint level, the forces will be acting around the joints. Joints do not compress. They compress a little bit in the joint capsule, but their main purpose is to rotate. For almost every joint in the human body, at least the ones that we care about, force acting around a point of rotation is a moment. This is a new word. A moment is what happens when a force acts through a distance to rotate something. And the moment is defined in physics as the force times the distance to the point of rotation, if you measure the distance in the right way, namely perpendicularly. We have two types of motion. We have straight line motion. We've talked about that last week. Force is proportional to the change in straight line momentum, which is the mass times the velocity vector. Then we have rotational motion. Force and distance multiplied together, moment, are proportional to the change in rotational momentum. Things have rotational momentum. You know this. If you start a ball spinning, it will continue to spin. Figure skaters, when they start to do their spins, they'll keep spinning. They'll actually play games using the equation we're about to talk about to change the rate of their spin. Force and distance are proportional to the change in rotational momentum, which is the moment of inertia, I, which I'll talk about momentarily, times the angular velocity. The moment of inertia, I, what it is a measure of how much mass there is and how far it is away from the center of rotation. So if you have a lot of weight far from the center of mass, if I spin you, you're going to have a big moment of inertia. It's going to be harder to spin you. If I load up a barbell and I put the great big CrossFit plates, the big bumpers on the end of the barbell, it's going to be harder to rotate that barbell than it is if I use iron plates that are closer to the center. Okay? So I is the moment of inertia and omega is the angular velocity. I gets bigger, the more mass is farther from the point of rotation. So we have these two equations. Force equals mass times acceleration. The linear momentum changes proportionally to the force. Now we have an analogous parallel equation, which is mass equals, pardon me, let me say it again. An analogous equation, which is moment equals the moment of inertia times the angular acceleration. So force, moment, mass, moment of inertia, acceleration, angular acceleration. It works just the same. The angular momentum changes proportionally to the moment. Force makes things accelerate. Torque, moment makes things spin. We have linear and rotational motion. Muscle acts around a point of rotation. Muscles always do this, almost always do this. They are rotators. The parallels to straight line motion, so we have, just to review, moment equals the moment of inertia times angular acceleration. We have force equaling the mass times the linear acceleration. Force is analogous to moment. The moment of inertia is analogous to mass. A, the acceleration vector in meters per second squared, is analogous to alpha, the rotational acceleration in degrees per second squared. If you have high moments of inertia, like this top, it will want to continue to spin. That's why it's constructed this way, so it has a lot of mass far away from the point of rotation. Now, let's do some practical applications. The moment is the force perpendicular to a line drawn from the point of rotation. If you multiply that force times that distance, you get the moment. So if d is this distance and F is the force, moment is F times d. And it's going to have to be perpendicular. The bigger the wrench, the more turning force you have. Some key points about moment. The bigger the moment arm, the bigger the moment. This is why we go to get bigger wrenches. Only the force perpendicular to the moment arm counts. That's the only force that actually rotates the thing. If you push a wrench onto the bolt, you don't rotate it. Moment is also a vector with a direction. We'll look at that more next week when we talk about the squat in more detail. And almost all actions of muscles in the body are moments. Muscles pull bones and make them rotate around joints. Moments are the primary means of human movement. So we have 3 wrenches here. The moment arms are perpendicular to the force. The moment arm, in this case, is from here to here, because that's already perpendicular. On this wrench, if you pull straight down on the wrench, you don't have as big of a moment arm. If you're actually going to use the wrench properly, you're going to pull this way. Okay? You'll get more turning force. Sometimes you have to turn a bolt in a tight spot and you can't really pull on it in the right direction. This case, this contributes no rotation to that bolt because that force is running right into the center of the bolt. That's pointless. What if we weld 2 wrenches together? In this case, the applied force is not perpendicular to the moment arm. So the distance from here to the point of application of the force, that's not perpendicular. What should we do? Well, there's a way to do it. There's actually 2 ways to do it. There's a hard way and an easy way. The harder way in this case is actually to resolve vectors into components and find the sum of perpendicular products. So you resolve the red vector into the yellow and the green, and you resolve the blue vector into the purple and the white. And then you multiply yellow times white, and so that's 1 moment arm, so it's this times that. and then you multiply the purple and the green. So this times that, the purple moment arm times the green force. And that would work. You add that together and you get the total moment. There is another way to do it. You can figure out the perpendicular distance from the point of rotation to the force vector. So you extend the line down here parallel to your force until you get to the point of rotation, and then you draw this line here. Okay? That would give you the total moment as well. So the total moment would be this force times the distance perpendicular to the force to the point of rotation. Okay? So you could consider this force, as long as it's acting anywhere on this line that is parallel with the force, it's going to do the same thing. So this is a conceptual way to think about it and figure out what's happening to that bolt with the welded wrench. Well, now if we consider in one of the lifts, the moments in the deadlift, the hip extensors pull around the hip joint. The knee extensors pull around the knee joint. The barbell moves in a straight line, but it moves in a straight line because of a combination of rotations. Muscles are moment makers. So you could see how those moments made that barbell move up. Moments and levers. The moment depends on the distance from the point of rotation, which for levers we'll call a fulcrum. If you increase the distance, you increase the turning power. If you decrease the distance, you'll increase the force that you need. So we can play games with this. If you have a wrench, down here by the bolt, you have a big force, a small distance, but you don't care because you're just trying to unstick the bolt. Out here, you have a small force moving through a big distance. You have to move your hand all the way around when you're using a wrench. But you don't care because you want to unstick the bolt. You're willing to trade this off. Moments are fun. You have the larger fella sitting out here with a shorter moment arm and the smaller fellow with the longer moment arm, and then they can both ride on the seesaw. You can also use levers to change the amount of motion. So if you really move this end, you can make this end really move fast and then pop the kid up in the air. So muscles work by means of levers, which are ways to trade moments for force and distance, really. The moment's proportional to the force and the distance. Less distance, more force. More distance, less force. You can trade it for increased motion. If you think about the biceps in the arm, the biceps doesn't contract very much, but the forearm moves a lot. There are 3 types of levers. In the class 1 lever, the effort is here. There's a fulcrum in the middle, and the resistance is here. And there aren't that many examples of it in the human body, but one of them is the semispinalis capitis, rotating the skull around the atlanto-occipital joint. So the back of the muscles in the neck pull on the skull and rotate it around the joint at the base of the skull. There's another example, the biceps femoris, your hamstring, rotates the pelvis and the torso against the load of the squat or the deadlift. So it rotates it around the hip joint. Class 2 lever, the effort's here, the resistance is here. So you're going to have more movement here, less movement here, and more force there. So the gastrocnemius and the soleus, that's in your calf. Pull up on the tubercle of the calcaneus, that's your heel. You stand up on your toes. It's a class 2 lever. Then we have the class 3 lever, the most common lever in the human body. So the resistance out here, the effort here. So for example, the biceps brachii, that's the biceps in your arm, attaches to the forearm at the radial tuberosity in the bicipital aponeurosis and rotates the forearm around the elbow. This is when you do your curls. So these are the 3 types of levers, and that concludes this set of slides.